This is a short video, but in this video, we're going to derive the parallel axis theorem. We've referred to it twice already, or at least several times already in some previous videos. The parallel axis theorem is something that you're going to use a lot in this class. You're going to use it a lot in mechanics materials. You use it in dynamics or mass moments of inertia. So it's something that you'll use a lot. So it's something that you need to understand. It's relatively straightforward, actually, but I like to, if the derivation is relatively straightforward for a formula, I like to do it, to derive it for my students so that you can see where it came from and the principles upon which it is based, rather than just accepting a formula and using it without truly appreciating it where it comes from. So we're going to derive the parallel axis theorem. This approximately follows Hibbeler's approach. So if you have a general area and you draw several axes through that area, A, B, C, D, E, and you could draw more. The moment of inertia about each of those axes is different. If CC is the centroidal axis, then, if we know that guy, can we find AA or can we find BB? That's the problem that we're looking at. So the picture we're going to draw looks like this. So we're going to draw an XY coordinate system. We're going to draw an area. We're going to put centroidal axes at the centroid of that area. So an X prime and a Y prime, those are centroidal axes. We're going to, and the X prime axis is a distance dy from X. And the Y prime axis is a distance dx from Y. Relative to this centroidal coordinate system, we're going to draw a little general dA area that's some Y tilde from the Y prime, or from the X prime axis, and that's some X tilde from the Y prime axis. And so we're going to just basically write an IX equation. So the moment of inertia about the x-axis is equal to the distance dy plus y tilde, that quantity squared, times dA. Pretty straightforward. So if we expand this guy, you get a dy squared plus a 2 dy times y tilde plus a y tilde squared dA. We expand this guy. Well, the 2 dy times the integral of y tilde dA goes to 0. The reason for this is because this is a centroidal set of axes. The moment of the area on one half of the area is positive, and the moment of the area on the other half is negative, and so they cancel one another out, so this guy is 0. This term is dy squared times the integral of dA, but the integral of dA is the area. And finally, this guy is the integral of y tilde squared dA. And so this is I bar about the X prime axis. And so finally, Ix is just I bar of this area about his X prime axis plus his area times the distance dy squared. Pretty straightforward. We typically write it as, Ix is equal to I bar plus AD squared. I usually drop the X prime subscript because the X bar implies a centroidal I. And so by adding the X prime is redundant, really, in my opinion. So I try to write it this way in most cases. And the dy squared is just, you would just call that y squared, or distance squared is what you'd call that. So if you look at this formula, the term AD squared is always positive. So I bar is a minimum, and as you move away from the centroidal axis, the I about those axes gets larger. And again, the AD squared term is a transfer term. It gets larger. Another way to think about it is, so remember, if you look at these original areas up here, an axis that passes approximately through the center of an area is going to have a low or smaller area moment of inertia. Because if you integrate y squared times all of the dAs, the average y of all of the dAs relative to the centroidal axis is smaller than for any other axis that you propose. And so you'd expect the centroidal axis to be a minimum axis or a small axis. This is an important point, and sometimes this is on an exam. So if you were given an area and an axis BB and an axis AA, and the question says, find they give you I about BB, for example, and they say, find AA. You cannot write the parallel axis theorem from one arbitrary parallel axis to another arbitrary axis. In other words, you can't write IAA is equal to IBB plus AD squared. So why is that? One of the terms has to be an I bar, has to be a centroidal axis. So you can write IBB is equal to I bar, which is ICC, plus AD squared. So this you can write one of the two sets of axes must be a centroidal axis. If you really want to go from BB to AA, you could do it in a two-step process. You could transfer the BB to the I bar, and then in the second step, transfer the I bar to the AA. So you can do it as a two-step process. But again, one of the two sets of axes has to be centroidal. And of course, these are parallel to one another. If you get to these axes at an angle, you're going like, wait a minute, this is a parallel axis theorem for parallel axes. What about these axes at some angle? Glad you asked that question. We will get to that here in a couple lectures. We'll actually derive an equation that lets us start with an IX, an IY, and product of inertia, and lets us rotate those guys to whatever angle you want. And so we will get there. So I'm glad you asked that question.